Every galaxy that we can see with a well-defined center seems to be hiding something enormous in its middle. Not a bright cluster of stars, not a glowing nebula, but an object so dense that light itself cannot climb back out of it once it gets too close. Astronomers call these objects supermassive black holes, and in some galaxies they weigh in at more than 1 billion times the mass of our Sun, all packed into a region smaller than our solar system. What is strange is not just that these things exist. What is strange is how closely tied they are to the galaxies that contain them. The mass of the black hole seems to track the mass of the stars around it, the speed at which those stars move, and even how orderly or chaotic their orbits are. For decades, the leading explanation was that galaxies grow their central black holes mainly by crashing into other galaxies. Newer evidence is complicating that story in a way that nobody fully expected, and it turns out we may have been missing most of the picture. To understand why that matters, it helps to start with what a black hole actually is, because the name itself causes a lot of confusion. People hear the words black hole and picture an empty gap in space, a kind of cosmic void where matter has vanished. That picture is backwards. A black hole is not an absence of matter. It is an overwhelming concentration of it. Some researchers prefer the term dark star because that description gets closer to the truth. A black hole is quite literally a mountain of matter, compressed down to the point where its gravity prevents any light from escaping. We cannot see it directly, not because there is nothing there, but because there is so much there that nothing, not even light, can climb back out once it crosses the boundary called the event horizon. The event horizon is the actual definition scientists use for where a black hole begins. It is not a physical surface you could touch. It is a boundary in space, a point of no return. Cross it, and every possible path forward leads only deeper. Physicists sometimes describe the inside of that boundary as a region of total unknowing, because no signal, no light, no information of any kind makes it back out to tell us what is happening within. Everything we can say about a black hole comes from watching what happens just outside that boundary, never from peering inside it. Most black holes form from the death of a massive star. A star spends most of its life converting hydrogen into helium through nuclear fusion, and that fusion process generates outward pressure that balances the inward pull of the star's own gravity. Once a sufficiently massive star exhausts its hydrogen fuel, it starts fusing heavier elements. Helium into carbon, carbon into oxygen, and so on, climbing the periodic table, step by step until it reaches iron. Iron is where the process stops being able to release energy through fusion. At that point, gravity finally wins, and the collapse happens catastrophically. The outer layers explode outward in a supernova, one of the brightest events the universe produces, while the core collapses inward past every point where any known force can stop it. What is left behind depends on the mass of that leftover core. For sufficiently massive stars, the collapse does not stop until a black hole has formed. All that complexity of carbon, oxygen, nitrogen, iron, every element that had been forged inside that star, gets crushed down into something we cannot see and cannot chemically analyze anymore. The information about exactly what elements went in is essentially erased. This erasure is not just a poetic way of describing black holes. It reflects something astonishingly simple about them as physical objects. A black hole, once formed, can be fully described using only 3 properties: its mass, its spin, and its electric charge. That is the entirety of what can be measured or known about it from the outside. You cannot ask how much iron went into a particular black hole versus how much hydrogen. All of that history is gone, hidden behind the event horizon forever. at least according to our present understanding of physics. Stellar collapse produces what astronomers call stellar mass black holes, typically around 10 times the mass of the Sun, though they can range higher depending on the star that produced them. Not every dying star produces a black hole. A star like our Sun, when it eventually runs out of fuel, is not massive enough to collapse into a black hole. Instead, it forms a white dwarf, a much less extreme object made of matter so dense that its own electrons are packed as tightly as physics allows, resisting further collapse. A white dwarf is, in a sense, a black hole's much gentler sibling. Only stars considerably more massive than the Sun end their lives collapsed all the way down into the true darkness of an event horizon. Supermassive black holes are an entirely different scale of object, and their origins are far less settled. These are the black holes that sit at the centers of galaxies, ranging from around 1,000,000 times the mass of the Sun up into the billions. Nearly every galaxy with a well-organized center appears to have one. That fact alone took decades of careful observation to establish. It is easy to say now, almost casually, that every galaxy has a central supermassive black hole. Behind that casual sentence is a mountain of research measuring the motions of stars and gas near galactic centers, inferring the presence of an unseen mass from how fast material orbits it. What makes supermassive black holes especially interesting is not just that they exist, but how tightly their properties track the properties of their host galaxies. Astronomers find a clear correlation between the mass of a central black hole and the total mass of stars in the surrounding galaxy, particularly in the dense central bulge of stars. There is also a correlation with how those stars move. In galaxies where stars orbit in smooth, ordered paths, the central black hole tends to be lighter relative to the galaxy. In galaxies where the stellar orbits are scrambled and disorganized, moving in many different directions rather than a single coherent rotation, the central black hole tends to be considerably heavier. This is a remarkably tight relationship, given that the black hole itself typically makes up less than 1% of the total mass of its galaxy. Something is linking the growth of this tiny, invisible object to the evolution of an entire galaxy of stars spanning hundreds of thousands of light years. For a long time, the leading explanation for that link was galaxy mergers, when two galaxies collide and merge into one. Individual stars almost never physically collide with each other, because space is so vast that even inside a galaxy, stars are spaced light years apart. Our own Sun's nearest stellar neighbor is around 4 light years away, and stars are correspondingly tiny compared to that distance. When two galaxies merge, most stars simply pass by each other, their relative positions shifting but their paths rarely intersecting directly. What does happen during a merger is a redistribution of angular momentum. Gravitational interactions during the merger disturb what were once smooth, ordered orbits and send both stars and gas tumbling inward toward the newly combined galactic center. That inward flow of material can feed the central black hole, growing its mass substantially. If both original galaxies had their own central black holes, those two black holes may eventually spiral together and merge as well, forming a single, more massive black hole. Mergers also tend to destroy the flat, ordered disk shape of a spiral galaxy, replacing it over time with a puffed-up, three-dimensional distribution of stars orbiting in many different planes, which astronomers call an elliptical galaxy. The picture that emerged from decades of study was elegant. Mergers scramble galaxies, feed black holes, and produce the tight correlation we observe between black hole mass and galaxy properties. For a long time, this was treated as essentially the whole story, recent research is complicating that elegant story. To test whether mergers were really the dominant driver of black hole growth, researchers began focusing on galaxies that show every sign of never having merged with anything. Galaxies that retain a pristine, flat spiral disk shape with no central bulge of chaotically orbiting stars. If the merger hypothesis were the whole story, these untouched, isolated galaxies should have correspondingly small central black holes on the lighter end of the supermassive range, since they never experience the merger-driven inflows of gas that theoretically fuel black hole growth. The measurements told a different story. When astronomers went out and carefully measured the central black hole masses in these pristine, undisturbed spiral galaxies, they found black holes far heavier than expected, in some cases approaching 1 billion times the mass of the Sun. These galaxies sat above the established correlation entirely, hosting black holes heavier than their stellar properties would predict, despite showing no evidence of ever having merged with another galaxy. Something else was clearly feeding these black holes, and it was not a merger. Researchers running large-scale cosmological simulations, essentially building a virtual universe from a starting cloud of hydrogen gas and letting the known laws of physics play out over billions of simulated years, tried to trace exactly where the material ending up inside simulated black holes actually originated. Their results suggested that mergers, whether the scrambling of gas or the direct merging of two black holes, accounted for only around 35% of the material feeding black hole growth in their simulations. Other independent simulation efforts found even smaller contributions from mergers, closer to 15%. Even taking the higher estimate, that still leaves the majority of black hole growth, somewhere around 2/3 or more, unexplained by mergers at all. If mergers are not doing most of the work, something else inside these galaxies must be responsible for taking material from calm, stable orbits and sending it plunging toward the center, before exploring what that something else might be. It helps to understand how we actually observe black holes growing in the first place, since a black hole, by definition, emits no light of its own. What we observe instead is the material falling into it. Because a black hole's gravity is so overwhelmingly strong, any gas or dust that strays too close does not simply fall straight in. It first settles into a swirling structure called an accretion disk, a flattened ring of material spiraling slowly inward. Material in that disk has to lose energy through countless collisions and friction before it can spiral close, enough to actually cross the event horizon. So accretion disks can persist for extremely long periods, continuously funneling matter inward. As this material spirals faster and faster, compressed and rubbing against itself under the tremendous gravitational pull, it heats up to extreme temperatures and begins to glow, often across many different wavelengths of light, from visible light all the way to intense radio and gamma radiation. This is exactly why the famous images of the material surrounding the black holes at the centers of the galaxy, Messier 87, and our own Milky Way, show a glowing ring with a dark shadow at the center. That glow is the accretion disk, not the black hole itself. And the shadow in the middle is the region blocked by the event horizon, in the most extreme cases, when a supermassive black hole is actively feeding on large amounts of surrounding gas. Its accretion disk can outshine the combined light of every star in its host galaxy. These objects were first identified decades ago as intensely bright points of light that looked almost like stars but showed strange properties inconsistent with any known star. They were nicknamed quasi-stellar objects, later shortened to the term astronomers still use today. and it was only with the launch of powerful space telescopes capable of resolving fine detail that scientists confirmed these brilliant points of light were sitting at the centers of entire galaxies, rather than being stars within our own galaxy. The extraordinary brightness came from an actively feeding supermassive black hole, its accretion disk glowing so intensely that it drowned out the light of every star surrounding it. Growth is not always a smooth, continuous process either. Black holes are not, despite popular imagination, endless vacuum cleaners capable of consuming anything nearby without consequence. Material falling toward a black hole has to fight its way in, colliding repeatedly to shed enough energy to actually spiral downward rather than simply orbiting indefinitely. If too much material gets crammed into the relatively small region around a black hole at once, pressure builds enormously, and the system can respond by expelling large amounts of energy and material back outward, in what astronomers sometimes describe informally as a burp. Sometimes this takes the form of a broad outward wind of hot gas and radiation. In galaxies with strong magnetic fields aligned with the black hole's spin axis, the ejected material can instead form narrow, focused jets streaming out from the black hole's poles at speeds approaching the speed of light. None of this ejected material actually comes from inside the event horizon, since nothing can escape from there. It comes from the extremely hot, energetic region surrounding the black hole, the accretion disk and its immediate environment. This feedback process is exactly how something as physically small as a black hole can influence an entire galaxy spanning hundreds of thousands of light years. To put the scale difference in perspective, if an entire galaxy was shrunk down to the size of a grain of sand, its central supermassive black hole would be smaller than a single atom. And yet the jets and winds that black hole can produce could, on that same shrunken scale, extend across the width of your entire hand. Despite being almost inconceivably small relative to its galaxy, and despite making up less than 1% of the galaxy's total mass, an actively feeding black hole can heat up or physically eject the cold gas that a galaxy would otherwise use to form new stars. In effect, by growing large enough and feeding energetically enough, a supermassive black hole can gradually shut down star formation across its entire host galaxy. Astronomers sometimes describe this bluntly as the black hole killing its galaxy, not through any deliberate process but simply as an emergent consequence of energetic feedback disrupting the cold gas reservoirs that stars need to form. This connects to one of the more striking distinctions astronomers draw between galaxy types. Broadly speaking, galaxies fall into two categories: star-forming galaxies still actively producing new stars, and what researchers sometimes call dead galaxies, ones that have largely or entirely stopped forming new stars. This distinction correlates strongly with galaxy shape. Spiral galaxies, the flat, ordered disk galaxies with graceful arms winding outward from the center, are much more likely to still be forming stars, with something like 70% of spiral galaxies actively forming stars and only around 30% having gone quiet. Elliptical galaxies, the puffed up, three-dimensional spheres of stars produced by mergers and other disruptive processes, show almost the opposite pattern, with around 90% of them essentially finished forming stars, and only about 10% still active. The question of why some galaxies stop forming stars while others keep going is one of the central open problems in galaxy evolution, and it connects directly back to black holes and mergers. Making new stars requires cold, calm gas. That might sound backward at first, since we tend to associate heat with energy and activity. But the physics works the opposite way. A star forms when gravity slowly pulls a cloud of gas together. clumping it denser and denser until pressure and temperature at the center ignite nuclear fusion. That gradual gravitational clumping only works if the gas is cold and relatively calm, with low internal energy, so that gravity can dominate over the random motion of gas particles. If a cloud of gas is heated up, its particles move faster and more chaotically, effectively fighting against gravity's attempt to pull everything together. Heated gas resists collapsing into new stars. This is why processes that heat up a galaxy's gas reservoir, whether through galaxy mergers, scrambling everything together, or an actively feeding black hole blasting out energetic winds and jets, tend to shut down future star formation, even without physically removing any material at all. Spiral galaxies and elliptical galaxies also seem to make the transition from actively star forming to quiet in very different ways. Spiral galaxies tend to fade slowly, gradually using up or gently heating their gas reserves over long timescales, transitioning gradually from a blue color associated with the hot, young, massive stars that dominate active star-forming regions, toward a redder color associated with older, cooler stars that dominate once star formation has slowed. This blue to red transition is sometimes described using the analogy of a flame. A very hot flame, like the blue flame from a gas burner, is actually hotter than the deep orange glow of dying embers in a fireplace. Even though everyday intuition often associates red with heat and blue with cold, elliptical galaxies, by contrast, tend to make their transition to a quiet, red, non-star forming state much more rapidly, often coinciding with the same violent merger event that reshaped their structure into that puffed-up spherical form in the first place. Interestingly, this transition does not appear to run only in one direction. There is growing evidence that some galaxies can be rejuvenated, reigniting star formation after a quiet period. If fresh cold gas finds its way back in, this might happen through a fresh infusion of gas cooling back down after being disturbed, or through the infall of a much smaller companion galaxy, dropping into the larger galaxy almost like a pebble dropped into a still pond, stirring things up and delivering new material capable of collapsing into stars. Galaxy evolution, in other words, is not necessarily a strict one-way march from young and star-forming toward old and quiet. It can, under the right conditions, run partly in reverse. Black hole feedback sits right in the middle of this debate, and it is not entirely clear that it only ever suppresses star formation. The same energetic outflows and jets that can heat up and disperse a galaxy's gas can, under certain circumstances, instead compress that gas through the shock waves they generate, potentially triggering bursts of new star formation along the path the shock travels. Researchers are still working through which effect tends to dominate, and under what conditions a black hole's feedback shuts a galaxy down versus stirring it back to life, setting mergers and feedback aside. The deeper mystery is what actually delivers the majority of material into a supermassive black hole in an otherwise isolated, undisturbed galaxy, since the simulations suggest mergers only account for a modest fraction of total growth. Several candidate mechanisms are under active investigation. One is the spiral arms themselves, the long winding structures that give spiral galaxies their name. These arms may act as funnels, gravitationally shepherding gas along their length, and gradually guiding it inward toward the galactic center over long stretches of time. Some spiral galaxies also contain a long, straight bar structure running through the center, with spiral arms emerging from each end of the bar rather than from the center directly. This bar structure is another strong candidate for funneling gas inward efficiently, and some simulations suggest it might be the single most effective internal mechanism for feeding a central black hole. Although this remains to be confirmed through direct observation, a third possibility reaches beyond the galaxy itself, out into the vast structure connecting galaxies across the universe, sometimes called the cosmic web. When astronomers map out the three-dimensional positions of galaxies across large volumes of space, a striking structure emerges, resembling something like a cosmic sponge, with dense clusters of galaxies concentrated at nodes, connected by long, thin filaments of galaxies and gas. Surrounded by enormous, nearly empty voids, there is evidence that gas can flow along these filaments, feeding directly into galaxies from the surrounding cosmic web, potentially supplying additional material that eventually finds its way down to the central black hole. Large-scale cosmological simulations reproduce this same filamentary structure when modeling the formation of the universe, lending support to the idea that this web plays a real role in feeding galaxies over cosmic time. There is also an open question of whether the dominant feeding mechanism has stayed the same throughout cosmic history, or whether it has changed over billions of years. Because light takes time to travel across the universe, observing a very distant galaxy means observing it as it existed billions of years in the past, effectively looking back in time. It is entirely possible that whichever mechanism dominates black hole growth in the relatively nearby, present-day universe was not the dominant mechanism billions of years ago, when the universe was younger, denser, and structured quite differently. Untangling which mechanism dominates, and whether that answer changes across cosmic history, remains one of the active frontiers of this entire field. Understanding exactly how black holes grow matters for reasons well beyond simple curiosity, though curiosity alone is a perfectly good reason to study almost anything. The growth history of supermassive black holes is deeply woven into the broader story of how galaxies evolve from the early chaotic universe into the ordered structures we see today. And galaxy evolution in turn feeds directly into cosmology, the study of how the entire universe has changed from its earliest moments up to now. Every piece of that puzzle helps complete the larger picture. There is also a longer, more practical thread running through this kind of research. Astronomy has repeatedly produced technologies that ended up transforming everyday life, often in ways nobody studying the night sky originally set out to achieve. Astronomers needed increasingly precise ways to measure exactly how much light was hitting their instruments, since older photographic plates only offered a rough, qualitative sense of brightness. That need drove the development of highly sensitive digital light detectors, technology that eventually became the foundation of the digital cameras now built into nearly every phone on the planet. Radio astronomers, needing to detect extremely long wavelengths of light using very large telescopes, developed techniques for combining signals from many smaller, distributed antennas into one much stronger combined signal. Those same signal combining techniques eventually found their way into modern wireless networking technology. Advanced telescopes generate enormous volumes of image data full of noise that needs to be carefully filtered and processed to reveal clean, usable images, and many of the image processing algorithms developed for astronomy have since been adapted for use in medical imaging, helping doctors extract clearer diagnostic images from noisy raw data. Even now, upcoming radio telescope projects capable of studying black hole feedback and outflows are expected to generate data faster than existing infrastructure can transmit or store it, pushing forward the development of faster data transfer technology that will likely ripple outward into other fields entirely unrelated to astronomy. From communications to finance, returning to the physics itself, one of the more surprising open questions is simply how large a black hole can grow before something fundamentally changes about how it grows. There appears to be an upper limit to how massive a black hole can become while still being observable through the traditional accretion disk method. To understand why, it helps to picture several distinct boundaries drawn around a black hole, each one further out than the last. Closest in is the event horizon itself, the true point of no return, where escape becomes impossible even at the speed of light. Slightly further out is a boundary astronomers call the innermost stable orbit, the closest distance at which something can still maintain a stable orbit around the black hole, rather than inevitably spiraling inward and being lost. This boundary effectively marks the inner edge of any accretion disk, since material any closer than this simply cannot maintain a stable orbit long enough to form a proper disk structure. Further out still lies a third boundary, sometimes called the self-gravitational radius. Beyond this distance, a cloud of gas is pulled more strongly by its own internal gravity than by the gravity of the central black hole. This matters enormously, because it is exactly why galaxies have stars at all, rather than every scrap of gas simply spiraling helplessly into the central black hole. Beyond the self-gravitational radius, clouds of gas can collapse under their own gravity to form stars, which then settle into stable orbits around the black hole rather than falling toward it. As a black hole grows more massive, both the event horizon and the innermost stable orbit expand outward, but they do not expand at the same rate as the self-gravitational radius. This creates the possibility that, for a sufficiently massive black hole, the innermost stable orbit can eventually push outward past the self-gravitational radius entirely. Once that happens, any gas approaching the black hole hits the self-gravitational radius before it ever reaches a point where it could form a stable accretion disk, meaning that gas simply collapses into new stars instead of ever spiraling down into the black hole. At that point, growth through the traditional accretion disk mechanism effectively stops. And because there is no more glowing accretion disk, the black hole also becomes essentially invisible to our usual observational methods. The exact point where this crossover happens depends on several factors, including how fast the black hole is spinning. A rapidly spinning black hole can push its innermost stable orbit closer in, allowing accretion disks to persist to somewhat higher masses before the crossover occurs. Current estimates put the theoretical upper limit for actively growing, observable supermassive black holes at somewhere around 100 billion times the mass of the Sun. One particular black hole, catalogued as an especially extreme example among known supermassive black holes, has been measured at around 60 billion times the mass of the Sun, remarkably close to that theoretical ceiling, because essentially all black holes are thought to retain at least some rotation inherited from the spinning gas that originally formed them. This spin-dependent boosting of the growth limit may be the only reason we can still observe accretion around such an extreme object at all. It raises an intriguing possibility that there could be even more massive black holes hiding at the centers of some galaxies. Black holes that grew large enough to shut off their own accretion disks and effectively vanish from view. Their true mass unknown simply because we have no way left to measure it. Between the well-studied stellar mass black holes, weighing in around 10 times the mass of the Sun, and the supermassive black holes found at galactic centers, weighing in from roughly 1 million to many billions of solar masses, there sits a strange, sparsely populated region astronomers call the intermediate mass gap. Very few confirmed black holes have been found with masses in the range of tens of thousands to hundreds of thousands of times the mass of the Sun. Several explanations have been proposed for this apparent gap. including the idea that whatever mechanism produced the earliest supermassive black holes may have allowed them to grow through this intermediate mass range extremely quickly, leaving few objects lingering there to be observed today. Detecting black holes in this mass range is also inherently difficult, since smaller black holes produce fainter accretion disks, making them much harder to spot at large cosmic distances. This intermediate mass gap remains one of the persistent, unresolved puzzles in the overall picture of black hole formation and growth. Beyond stellar mass and supermassive black holes, there is a purely hypothetical category that has captured a great deal of scientific imagination, known as primordial black holes. Unlike every other type of black hole discussed so far, primordial black holes are not thought to have formed from the collapse of a dying star. Instead, the idea traces back to the extremely early universe, a time when all matter existed as an incredibly dense, turbulent mixture, long before stars or galaxies had formed. In that environment, it is theoretically possible that random fluctuations in density could have caused certain regions of matter to spontaneously clump together, tightly enough to collapse directly into black holes, without ever passing through the intermediate stages of star formation and supernova explosion that produce ordinary stellar mass black holes. If this process happened at all, it could have produced an enormous number of extremely small black holes scattered throughout the early universe, with masses ranging anywhere from a tiny fraction of a gram up to roughly the mass of an entire planet. One of the more tantalizing ideas connected to primordial black holes is that they might make up some or all of the mysterious substance known as dark matter, the invisible mass that appears to vastly outweigh all the ordinary visible matter in the universe. This idea has attracted considerable research attention, and there is some observational evidence that fits reasonably well with it, though there is also evidence that seems to argue against primordial black holes, accounting for all of the dark matter in the universe. One line of supporting evidence comes from large-scale surveys that monitor the brightness of enormous numbers of stars over time, watching for stars whose brightness naturally varies due to pulsation or the periodic dimming caused by orbiting planets passing in front of them. Occasionally, researchers spot an extremely brief, unexplained brightening of a star, consistent with an invisible object passing directly between us and that star and briefly acting as a gravitational lens, bending and magnifying its light for a fleeting moment. Some researchers have proposed that these brief lensing events could be caused by passing primordial black holes, though this evidence remains far from conclusive, and primordial black holes remain an entirely hypothetical class of object for now. Adding to the difficulty of ever confirming primordial black holes, there is a competing theoretical process by which black holes are thought to slowly lose mass over extraordinarily long timescales, a phenomenon known as evaporation, tied to a concept called Hawking radiation, named for the physicist who first worked out the theory behind it. According to Einstein's famous equivalence between energy and mass, any mass locked away inside a black hole should, in principle, remain trapped there permanently, unless there exists some mechanism by which the black hole can gradually radiate energy away and, in doing so, slowly shrink. Hawking radiation proposes exactly such a mechanism rooted in quantum physics. Right at the boundary of the event horizon, quantum effects can spontaneously produce pairs of particles, one of which falls into the black hole while its partner escapes outward as radiation. Over unimaginably long timescales, this process would very gradually drain mass and energy away from the black hole, causing it to shrink and eventually, in principle, evaporate away entirely. The predicted rate of this radiation is extraordinarily slow for any black hole of realistic astrophysical size. So slow that no direct detection of Hawking radiation has ever been achieved. And many researchers remain doubtful it will ever be directly measurable given how faint the resulting signal would be. Even from a large collection of primordial black holes concentrated somewhere like the center of our galaxy, there is one particularly playful hypothesis connecting primordial black holes to something much closer to home. Astronomers have long noticed subtle gravitational disturbances affecting the orbits of certain distant objects at the edge of our own solar system. Disturbances that hint at the presence of an as yet undiscovered planet, sometimes informally referred to as a ninth major planet, occupying the solar system's distant outer reaches. Extensive searches for this hypothetical planet have so far come up empty, in part because an object that far from the sun would reflect very little sunlight and would need to be detected. Instead, through faint infrared heat emission, an inherently difficult observational challenge. Given the repeated failure to spot any conventional planet out there, a small number of researchers have floated an unusual alternative explanation: that the disturbing mass might not be an ordinary planet at all, but rather a primordial black hole with roughly 10 times the mass of Earth, compressed down to the physical size of a small ball. If that speculative idea ever turned out to be correct, it would offer an extraordinary nearby opportunity to search directly for Hawking radiation, and conceivably even to send a spacecraft to study the object up close, testing our understanding of extreme gravity in our own cosmic backyard. This remains a highly speculative idea resting on a great many unconfirmed assumptions, but it illustrates just how far-reaching the implications of black hole physics can become, extending all the way from the centers of distant galaxies to the unexplored edges of our own solar system. Black holes matter to physics for another, deeper reason as well. Beyond their astrophysical role in shaping galaxies, they represent the most extreme laboratories available anywhere for testing our fundamental theories of gravity. Historically, physics has advanced precisely at these kinds of extremes, where existing theories start to break down under conditions more intense than the ones they were originally built to describe. Newton's theory of gravity worked extraordinarily well for centuries, describing the motion of planets and falling objects with remarkable precision. It was only when astronomers examined the orbit of Mercury, the planet closest to our Sun and therefore subject to the strongest gravitational field in the solar system, that a small but persistent discrepancy showed up between Newton's predictions and what was actually observed. That discrepancy was eventually resolved by Einstein's theory of general relativity, which correctly accounts for the subtle effects of gravity in stronger gravitational fields than Newton's theory was designed to handle. Black holes push that same logic to its absolute extreme. Nowhere else in the universe is space curved as intensely, and nowhere else is gravity as powerful. If general relativity is ever going to break down in a testable way, the environment immediately surrounding a black hole is the most promising place to look for cracks. This is precisely what makes recent direct imaging of black holes so scientifically valuable. The images captured of the material surrounding the supermassive black holes at the centers of the galaxy, Messier 87 and our own Milky Way, are not simply pretty pictures. They are precise scientific measurements, allowing researchers to directly compare the observed behavior of glowing material near the event horizon against the specific predictions. General relativity makes for that environment. So far, every test has continued to match Einstein's predictions closely, reinforcing confidence in general relativity even in the most extreme gravitational environment we can currently observe. But researchers continue pushing these tests further because a confirmed discrepancy, however small, could point the way toward a deeper theory of gravity. That deeper theory is exactly what many physicists hope black hole research might eventually help reveal. A long-sought unification between general relativity and quantum physics, sometimes called quantum gravity. These two pillars of modern physics work extraordinarily well within their own separate domains. General relativity describes gravity and the large-scale structure of the universe with remarkable precision. Quantum physics describes the behavior of particles and forces at the smallest scales with equally remarkable precision. The trouble is that the two theories have never been fully reconciled into a single, unified framework, and black holes sit right at the uncomfortable intersection between them. Since they combine the deepest gravitational extremes with quantum-scale physics happening right at the event horizon, many researchers suspect that a full understanding of black holes, along with a full understanding of the very earliest fractions of a second after the universe began, will require exactly this kind of unified quantum theory of gravity, one that does not yet exist, but that a great deal of ongoing research is actively working toward. Alongside black hole physics, this broader conversation inevitably touches on dark matter, another one of the more misunderstood ideas in modern astrophysics. It is entirely reasonable to feel skeptical about a substance that, by definition, cannot be directly seen or detected through any electromagnetic interaction whatsoever. Dark matter, as the name suggests, does not absorb, emit, or otherwise interact with light in any way, meaning it does not interact with the electromagnetic force, one of the small handful of fundamental forces recognized in physics alongside gravity, the strong nuclear force and the weak nuclear force responsible for radioactive decay. Framed that way, dark matter is not actually as exotic an idea as it might initially sound. It simply does not interact with one particular force, in much the same way that certain stable elements do not meaningfully interact with the weak force governing radioactivity. A useful, if imperfect, everyday comparison is the wind. Nobody can see wind directly, and yet its existence is obvious from its effects, the way it bends trees and stirs loose objects. In a similar way, astronomers infer the existence of dark matter almost entirely through its gravitational effects on things we can see. One of the strongest pieces of evidence comes from gravitational lensing, a direct consequence of Einstein's general relativity. According to that theory, any sufficiently massive object curves the surrounding fabric of space itself, and light traveling through that curved space follows a bent path rather than a straight line. When a massive galaxy or an entire cluster of galaxies sits directly between us and more distant background galaxies, the light from those background galaxies gets bent and distorted on its way to us, producing visibly warped or smeared images rather than the galaxy's true undistorted shapes. By carefully measuring exactly how much that light has been warped, astronomers can calculate precisely how much mass must be present to produce that particular amount of curvature. When that calculation is carried out, the resulting mass consistently comes out far larger than the combined mass of every star, every cloud of gas and dust, and every known dark object like a black hole that could plausibly be present, often by a factor of 5 to 10 times more mass than can be directly accounted for. A second major line of evidence comes from large-scale cosmological simulations, the same kind of virtual universe modeling mentioned earlier in connection with black hole growth. When researchers run these simulations using only the ordinary matter we can directly observe, without including any additional invisible mass, the resulting simulated universe simply does not produce galaxies that resemble the ones we actually observe around us. Some additional gravitational scaffolding, provided by an invisible form of matter, appears necessary to explain how galaxies could have clumped together into the structures we see today. Both of these lines of evidence, gravitational lensing and large-scale structure simulations, ultimately depend on trusting that general relativity correctly describes gravity under these circumstances. A meaningful body of researchers is actively exploring alternative theories of gravity, specifically to see whether an altered theory of gravity, rather than an invisible new form of matter, could explain the same observations without requiring dark matter at all. So far, none of those alternative theories has managed to explain the full range of observations as successfully as general relativity, combined with dark matter, does, which is why dark matter remains the leading explanation, not because scientists are especially attached to the idea, but because it continues to be the best fit for the evidence collected so far. If a better explanation ever does emerge, most researchers would treat that as a triumph rather than a defeat, a genuine advance in understanding rather than an embarrassing correction. It is worth remembering that dark matter itself was an extremely reluctantly accepted idea when it was first proposed, taking decades of accumulating evidence before the wider scientific community came to accept it as the best available explanation. Some of the most surprising recent challenges to our understanding of black holes and galaxy formation have come from the James Webb Space Telescope, whose extraordinary sensitivity has allowed astronomers to peer further back into the early universe than ever before. One unexpected discovery involves the shapes of very distant, and therefore very early, galaxies. Based on earlier theoretical models, astronomers generally expected the early universe to be extremely chaotic, dominated by frequent galaxy mergers and irregular, disordered galaxy shapes, with well-ordered spiral disks only emerging gradually after billions of years of settling down. Instead, observations kept turning up well-formed spiral disk galaxies at surprisingly early points in cosmic history, and then even earlier examples, and then earlier still. This has forced a significant reconsideration of how quickly galaxies can settle into the calm, ordered rotating structures we associate with mature spiral galaxies today, suggesting that this transition from chaos to order may have happened considerably faster and considerably earlier than previously assumed. An even more direct challenge involves the sheer size of some of the black holes discovered at these early cosmic epochs. As discussed earlier, black hole growth through the accretion disk process has physical speed limits, since too much infalling material builds up pressure and triggers energetic outflows that can temporarily throttle further growth. Given those limits, there should be a minimum amount of time required for a black hole to grow from the modest mass produced by an initial supernova, around 10 times the mass of the Sun, up to the much larger mass threshold that qualifies as at least 1,000,000 times the mass of the Sun. And yet James Webb has repeatedly found black holes with masses already in that supermassive range at points remarkably early in cosmic history, in some cases within less than 1 billion years of the universe's beginning, a span of time that seems uncomfortably short for the standard growth process to have produced such a massive object, starting from an ordinary stellar remnant. This tension has led many researchers to seriously consider an alternative formation pathway for at least some of the earliest supermassive black holes, one that skips the intermediate steps of star formation and supernova collapse entirely. Under this alternative model, sometimes called direct collapse, an especially massive and dense cloud of primordial gas in the very early universe could, under the right conditions, collapse directly into a black hole without ever first condensing into an ordinary star. A black hole formed this way could start out already far more massive than a typical stellar remnant, potentially explaining how some black holes manage to reach supermassive status so quickly after the universe began. This idea connects directly back to the earlier discussion of different possible pathways for feeding black hole growth. Since a universe containing more well-formed disk galaxies earlier than expected, alongside black holes that started out unusually massive from the beginning, opens up new and more efficient growth pathways that current research is still working to fully understand. Separately from questions of early galaxy shape and black hole mass, James Webb has also turned up an entirely unexpected and still not fully explained population of objects that researchers have informally nicknamed little red dots. These objects were originally found by astronomers specifically searching for signatures of actively growing black holes within James Webb's data, using a particular observational technique. When light from a galaxy is spread out into its full spectrum, its constituent colors or wavelengths, specific chemical elements like hydrogen or oxygen typically produce very sharp, narrow spikes of brightness at precisely defined wavelengths. When that same light comes from hydrogen gas spiraling rapidly around a black hole in an accretion disk, however, those normally sharp spikes get smeared out into much broader features. This broadening happens because gas on one side of the accretion disk is moving rapidly toward us while gas on the opposite side is moving rapidly away. And that relative motion shifts the light's wavelength through the same physical effect that causes an ambulance siren to sound higher pitched as it approaches and lower pitched as it recedes. Applied to light rather than sound, motion toward an observer shifts the light toward bluer wavelengths, while motion away shifts it toward redder wavelengths, and the combination smears what would otherwise be a sharp spectral spike into a broad, blurred feature. Astronomers went looking for exactly this kind of broadened spectral signature as a marker of actively feeding black holes, and in the process kept turning up strange, extremely compact, very red objects, far more of them than anyone anticipated. The puzzle deepened once researchers examined the spectra of these little red dots more closely. Not all of them showed the expected broadened emission signature associated with gas swirling around a black hole. Many showed an unusual overall shape to their spectrum instead, with relatively more light at both the blue and red ends of the spectrum, but comparatively less in the middle. An unusual pattern not easily explained by either an ordinary galaxy or a straightforward feeding black hole on its own. One leading explanation, currently under investigation, is that these objects may represent actively growing black holes embedded within an unusually dense, dusty cocoon of surrounding gas, with that dense gas absorbing and re-emitting the light from the underlying accretion disk in a way that produces this distinctive, unexpected spectral shape. The full explanation for the little red dot population remains an active and genuinely unresolved area of research, illustrating how much can still be discovered even about something as extensively studied as actively feeding supermassive black holes. These kinds of discoveries also raise a broader and somewhat unsettling question. If black holes are primarily detected through the glowing accretion disks that surround them, what about black holes that are not actively feeding at any given moment? Current estimates suggest that only around 10% of supermassive black holes are actively growing and therefore visible through this method at any given time. The rest sit quietly at the centers of their galaxies, invisible to our usual detection methods. Their masses and properties essentially unknown unless some other indirect method, such as measuring the motion of nearby stars, can reveal their presence. Combined with the earlier discussion of extremely massive black holes potentially crossing the threshold, where their accretion disks shut off entirely, it becomes clear that a substantial and genuinely unknown population of supermassive black holes may exist throughout the universe, hidden simply because we currently lack the tools to detect them. Fortunately, the tools available to astronomers are rapidly improving, and a new generation of observatories promises to reshape our understanding of black hole growth over the coming years. A newly operational survey telescope built high in the mountains of Chile represents one of the more significant recent additions to this effort. Rather than focusing deeply on a single small patch of sky, this observatory is designed to repeatedly scan the entire visible sky, capturing a fresh image of everything it can see roughly every few nights. This kind of repeated, wide-field monitoring is extraordinarily valuable for studying black holes, because an accretion disk is never a static, unchanging object. It constantly varies in brightness as the rate of infalling material fluctuates, sometimes gradually and sometimes dramatically. Having continuous, repeated brightness measurements for every known, actively feeding black hole across the observable sky represents an enormous leap forward compared to the more limited snapshots available previously, essentially transforming our view of black hole variability from a handful of occasional still photographs into something closer to continuous video footage across the entire population of known actively growing black holes, rather than just a small handful of well-studied examples. A separate space telescope, recently launched by the European Space Agency, is tackling a complementary challenge, mapping out the precise shapes of enormous numbers of galaxies across very large areas of sky with exceptional clarity and resolution. This matters enormously for understanding black hole growth, because, as discussed earlier, the shape of a galaxy encodes crucial information about its history, revealing whether it has experienced a disruptive merger in the past or remained a calm, undisturbed spiral disk throughout its life. This new telescope is expected to resolve fine structural details, like the presence or absence of a central bulge, or subtle bar structures running through a galaxy's disk, across vastly more galaxies and vastly more sky than has previously been possible, turning what used to appear as fuzzy, ambiguous blobs from ground-based telescopes into crisp, clearly resolved structures suitable for detailed structural classification. Radio astronomy is also entering a new era, with a major next-generation radio telescope array currently under construction, designed in part specifically to study the outflows and jets produced by feeding black holes in far greater detail than has previously been achievable. Radio observations are particularly well suited to tracing the large eye-scale structure of jets and outflows as they travel outward through a galaxy, since much of the radiation produced by these energetic ejections falls specifically within radio wavelengths. This upcoming facility is expected to generate such enormous volumes of data that existing infrastructure for storing and transmitting scientific data may struggle to keep pace. An engineering challenge in its own right that researchers are actively working to solve, and one that, much like earlier astronomical innovations, may end up producing spin-off technologies with applications well beyond astronomy itself. Taken together, this next generation of observatories promises a substantially more complete picture of black hole growth than has ever been available before, where researchers previously had to rely on limited, static snapshots and painstaking individual case studies. The coming years should provide continuously updated brightness data for enormous numbers of actively feeding black holes, exceptionally sharp structural classifications for enormous numbers of host galaxies, and much more detailed observations of the outflows and jets these black holes produce. Rather than resolving the open questions discussed throughout this examination, these new instruments are likely to sharpen them considerably, providing far more precise answers to exactly which growth mechanisms dominate, how efficient each one actually is, and whether the dominant mechanism has genuinely changed across cosmic history. Closer to home, this entire field of research eventually circles back to a very personal question: the eventual fate of our own galaxy and its own central supermassive black hole. The most significant event on the horizon for the Milky Way is its eventual collision and merger with its nearest large galactic neighbor, the Andromeda Galaxy, sometimes catalogued by astronomers under an alternate designation. Andromeda currently sits at a distance of roughly 2.5 million light-years from us. But the two galaxies are gradually drawing closer together under their mutual gravitational attraction, and current projections suggest the Milky Way and Andromeda will begin merging together in roughly 5 billion years. When that merger happens, it will scramble the elegant spiral structure of both galaxies in exactly the way described earlier in this discussion of mergers, redistributing stars, gas, and angular momentum throughout the combined system. Whether the end result will be a single, puffed-up, elliptical galaxy, or something that retains more of a disk-like structure, remains genuinely uncertain, depending heavily on the precise angle at which the two galaxies collide, how many separate close passes they make before fully merging, since galaxies involved in this kind of merger often swing past each other multiple times before settling into a final combined structure, and whether any additional nearby galaxies become gravitationally entangled in the process as well. The central black holes of both galaxies are expected to play their own dramatic role in this eventual merger. As the two galaxies combine, their respective central supermassive black holes should gradually spiral toward each other as well, eventually merging into a single, considerably more massive black hole at the center of the newly combined galaxy. Depending on how much gas gets funneled inward during this chaotic process, that newly merged black hole could experience a substantial burst of feeding activity, potentially triggering exactly the kind of energetic outflow or burp described earlier in this discussion, releasing intense radiation out through the surrounding galaxy. This raises a genuinely open question about what happens to our own solar system throughout this entire process, both in terms of where it ends up positioned within the newly reshaped combined galaxy after all of this gravitational sloshing and redistribution settles down, and whether it might be exposed to any of that intense radiation released by the newly merged and potentially highly active central black hole. There is even a compelling argument that the relatively quiet, modestly sized black hole currently sitting at the center of the Milky Way may have played an important, if indirect, role in allowing complex life to develop on Earth in the first place. If our galaxy's central black hole had gone through a major energetic feeding episode within the roughly 4 billion years since life first began evolving on our planet, the resulting burst of radiation could plausibly have disrupted the stable conditions life requires to develop and persist over such long stretches of time. Instead, our galaxy appears to have remained one of the calmer, relatively undisturbed examples throughout that critical stretch of time, its central black hole quietly present but not violently active. And that relative calm may have been an important, if easily overlooked, precondition for our own existence. It is worth stepping back for a moment to appreciate just how strange the theoretical history of black holes actually is, because the idea existed on paper for a remarkably long time before anyone found convincing observational evidence that such objects were real. When Einstein published his theory of general relativity, describing gravity as the curvature of space and time caused by mass and energy, a physicist working out exact mathematical solutions to Einstein's equations discovered within the same year that those equations permitted an object so dense that nothing, not even light, could escape its gravitational pull once inside a certain radius. For decades afterward, this result was treated by many physicists, including Einstein himself at times, as a strange mathematical curiosity rather than a description of anything that could plausibly exist in nature. It took additional theoretical work, including calculations establishing a precise mass limit above which a collapsing stellar core cannot be held up by the pressure of tightly packed electrons and must continue collapsing further, to convince the physics community that the collapse of sufficiently massive stars really could produce these strange, light-trapping objects in reality, not merely on paper. Even the modern name for these objects, the term black hole itself, only came into common usage decades after the underlying mathematics had already been worked out, replacing a variety of earlier and more cumbersome, descriptive terms that researchers had been using before that for most of the 20th century. Black holes remained objects inferred indirectly through their gravitational influence on visible companions or through the glow of material falling into them, rather than objects observed directly in any more immediate sense. That began to change dramatically with the development of gravitational wave astronomy, an entirely new way of detecting black holes that does not rely on light at all. According to general relativity, extremely violent gravitational events, such as two black holes spiraling together and merging into one, should send ripples through the very fabric of space and time itself. Gravitational waves that propagate outward at the speed of light, stretching and compressing space by an almost unimaginably tiny amount as they pass. Detecting a distortion thus small requires instruments of extraordinary precision. But exactly this kind of detector was eventually built, using long, precisely controlled laser beams to measure minuscule changes in distance far smaller than the width of a single proton. The first confirmed detection of gravitational waves from two merging black holes marked an entirely new observational window onto the universe, allowing researchers to directly detect black hole mergers happening in galaxies far too distant and too faint to observe through light alone. Since that first detection, numerous additional black hole mergers have been recorded this way, each one providing an independent and remarkably direct test of general relativity's predictions in exactly the kind of extreme gravitational environment discussed earlier. Since the pattern of ripples produced during a merger encodes detailed information about the masses, spins, and dynamics of the two merging black holes, gravitational wave detections have also helped fill in some of the uncertainty around exactly how stellar mass black holes form and how large they can typically grow through stellar collapse alone, since the masses measured from merging pairs of black holes sometimes turn out to be larger than many earlier theoretical models predicted for objects formed through ordinary supernova collapse. This has fed back into the broader puzzle of the intermediate mass gap discussed earlier, raising interesting questions about whether repeated mergers of smaller black holes merging with other black holes over successive generations, might themselves be one of the pathways that eventually produces intermediate mass black holes, or perhaps even contributes to the early seeds that grow into some of the earliest supermassive black holes observed by the James Webb Space Telescope. Beyond mergers and steady accretion, black holes occasionally reveal themselves through a much more dramatic and violent event, when an unlucky star wanders too close to a supermassive black hole and gets torn apart by the black hole's immense tidal forces. Because gravity grows stronger the closer an object gets to a massive body, the side of a star facing the black hole experiences noticeably stronger gravitational pull than the side facing away. And if a star strays close enough, this difference becomes so extreme that it literally stretches and eventually shreds the star apart. A process researchers sometimes describe using the same term applied to the fate of any object falling too deep into a black hole's gravitational grip: a stretching and shredding effect. Roughly half of the star's disrupted material typically gets slingshotted away entirely, while the remaining half falls inward toward the black hole, producing an intense, temporary flare of light as that stellar material is rapidly consumed. These events, sometimes called tidal disruption events, offer astronomers a rare and valuable opportunity to directly measure the properties of an otherwise quiet, non-feeding black hole, one that would ordinarily remain completely invisible, briefly lit up by the unfortunate star that wandered too close. This brings us back to one of the deeper theoretical puzzles tied up in the fact that a black hole can be completely described using only three numbers: its mass, its spin, and its electric charge. Physicists refer to this remarkable simplicity as the no-hair theorem, the idea that a black hole retains no other distinguishing features, no matter how complex or varied the material that originally fell in to form it. Whether a black hole formed from the collapse of a star made mostly of hydrogen, or from a star with a completely different internal composition, or from the merger of several smaller black holes, the resulting object looks identical from the outside as long as its mass, spin, and charge happen to match. All the additional detail, every bit of information about exactly what fell in and in what order, appears to be erased. This apparent erasure of information creates a genuinely uncomfortable tension with one of the deepest principles in quantum physics: the idea that information about a physical system should never be truly destroyed, even if it becomes so scrambled and inaccessible that reconstructing it in practice is impossible. If a black hole truly erases all information about what fell into it, and if that black hole eventually evaporates away entirely through Hawking radiation, as discussed earlier, then it seems as though the information that fell in the first place would be permanently and irrecoverably lost, in apparent violation of that fundamental quantum principle. This tension, often referred to as the black hole information paradox, has occupied theoretical physicists for decades, and it remains formally unresolved. Various proposed resolutions suggest that the information is not actually lost at all, but instead gets encoded in remarkably subtle correlations within the radiation that gradually escapes the black hole over its evaporation lifetime, though working out the precise mechanism by which that could happen, in a way fully consistent with both general relativity and quantum physics, remains one of the most actively studied problems at the boundary between the two theories, and one of the strongest hints that a full theory of quantum gravity will be needed to finally resolve it. Spin, one of the three defining properties of any black hole, deserves a bit more attention as well, since it plays such an important role in several of the topics already discussed, from boosting the maximum observable mass of a supermassive black hole to shaping the direction and power of jets launched from its immediate surroundings. Measuring a black hole's spin observationally is considerably more challenging than measuring its mass, since spin does not straightforwardly announce itself the way a strong gravitational pull on nearby stars does. Instead, researchers typically infer spin by studying subtle distortions in the spectrum of light emitted from the innermost, hottest regions of an accretion disk, regions whose exact distance from the black hole depends sensitively on how fast the black hole itself is spinning. A rapidly spinning black hole drags the fabric of space around with it in its immediate vicinity, an effect general relativity predicts, and that has been confirmed through exactly this kind of detailed spectral analysis, allowing the innermost stable orbit to sit closer to the event horizon than it would for a non-spinning black hole of the same mass. This is the physical basis for the Earlier claim that spin allows a black hole to keep growing to somewhat higher masses before the innermost stable orbit finally overtakes the self-gravitational radius and shuts off further growth through accretion. The question of exactly how the very first black hole seeds formed, the initial objects that eventually grew into the billion solar mass giants observed at the centers of galaxies today, remains deeply entangled with the discussion of early universe conditions raised earlier in connection with James Webb's surprising discoveries. In the standard picture, the earliest stars to form in the universe were likely far more massive than typical stars forming today, since the primordial gas available to form them lacked the heavier elements that, in the modern universe, tend to fragment collapsing gas clouds into many smaller stars rather than one enormous one. These extremely massive early stars would have burned through their fuel quickly and collapsed into correspondingly massive black hole seeds upon their deaths, seeds that could then grow further through subsequent accretion and mergers. The competing direct collapse pathway discussed earlier proposes an alternative route entirely, skipping stellar formation altogether, and instead collapsing an unusually massive, pristine cloud of primordial gas directly into a black hole, seed that starts out dramatically more massive than anything produced by ordinary stellar collapse. Distinguishing observationally between these two competing origin stories, and determining whether one, the other, or some combination of both actually explains the population of surprisingly massive early black holes that James Webb keeps turning up, remains one of the most actively pursued open questions in this entire field, one that upcoming observatories are specifically designed to help address. It is worth explaining briefly how astronomers actually measure the mass of a supermassive black hole in the first place, since the black hole itself emits no light and cannot simply be weighed directly. The most common approach relies on watching how fast stars or gas move in the immediate vicinity of a galaxy's center. According to the same physics that governs planetary orbits within our own solar system, an object orbiting a large central mass moves faster the more massive that central object is for a given orbital distance. By carefully measuring the velocities of stars or gas clouds orbiting close to a galaxy's center, and combining that with their distance from the center, astronomers can calculate the mass required to hold those orbits together gravitationally. When that calculation is applied to the crowded region right at a galaxy's center, the resulting mass is often so large and so tightly concentrated into such a small volume that no other explanation fits besides an enormous, compact, essentially invisible object, precisely the signature of a supermassive black hole. This technique has been applied successfully to our own galaxy's central black hole, tracking individual stars as they trace out extremely tight, fast orbits around an apparently empty point at the galaxy's exact center, providing one of the most direct and convincing pieces of evidence yet gathered for the existence of the black hole at the heart of the Milky Way. This same orbital tracking method is also how astronomers originally established the tight correlation discussed earlier between black hole mass and the properties of the surrounding galaxy, since it allows researchers to measure black hole masses across large numbers of nearby galaxies and directly compare those measurements against each galaxy's total stellar mass, the mass concentrated in its central bulge, and the overall pattern of stellar motion throughout the galaxy. It was exactly this large-scale comparison, built up gradually over many years of painstaking individual measurements across many different galaxies, that first revealed just how consistently a galaxy's central black hole mass tracks its broader stellar properties, a correlation tight enough that it strongly suggested some kind of genuine physical connection between the growth of the black hole and the evolution of its host galaxy, rather than being some kind of statistical coincidence. The direct imaging efforts that produced the now well-known pictures of the material surrounding the black holes in the galaxy Messier 87 and our own Milky Way represent a genuinely enormous international collaborative effort, linking radio telescopes scattered across multiple continents into a single, effectively planet-sized virtual telescope. Because the black hole's shadow appears so small when viewed from Earth, an ordinary single telescope, no matter how large, would not have nearly enough resolving power to make out any detail at all. By combining signals recorded simultaneously at widely separated telescopes around the globe, using extraordinarily precise atomic clocks to synchronize the recordings and sophisticated computational techniques to combine the data afterward, researchers were able to effectively simulate a telescope with a dish the size of the entire Earth, just barely large enough to resolve the glowing ring of material surrounding these two black holes and the dark shadow cast by their event horizons. Researchers involved in this collaboration have continued expanding the network, adding additional telescopes and refining their techniques, with plans already underway to produce sharper images in the future, potentially resolving finer structural detail within the glowing material, and perhaps even capturing subtle changes over time as the accretion disk itself evolves, offering an increasingly detailed, almost video-like view of the immediate environment surrounding these extreme objects. Placing all of this research within the broader arc of cosmic history helps clarify why the timing puzzles raised by James Webb's early black hole discoveries feel so significant to researchers working in this field. In the standard picture of cosmic history, the universe began in an extremely hot, dense state and expanded and cooled over time. For a considerable stretch after that beginning, ordinary matter existed as a hot, ionized plasma, opaque to light, until the universe cooled enough for electrons and atomic nuclei to combine into neutral atoms, allowing light to finally travel freely for the first time, producing the faint background glow that fills the entire sky today and that researchers use as one of their most precise tools for studying the early universe. After that point, the universe entered a long stretch, sometimes referred to as the cosmic dark ages, since no stars yet existed to produce light of their own, before gravity gradually pulled the first clumps of gas together densely enough to ignite the very first generation of stars, and shortly afterward, the very first galaxies. It is within this early window, only a few 100 million years after the universe began, that James Webb has been finding both surprisingly well-formed disk galaxies and surprisingly massive black holes, both showing up earlier than standard models anticipated. Understanding exactly how structure formation proceeded so efficiently during this early period remains one of the most active and rapidly evolving areas of modern astrophysics, with black hole growth sitting right at the center of that broader puzzle. Taking a step back from the specific mechanisms and measurements, it is worth appreciating just how much the overall picture of black holes has shifted, even within a relatively short span of research history. Not so long ago, the very existence of black holes was treated with considerable skepticism, even by some of the physicists whose own equations predicted them. Then came decades of indirect evidence, orbiting companions being tugged around by an invisible mass, bright quasars blazing from the centers of distant galaxies, and precise stellar orbits tracing out empty points at galactic centers. Then came direct imaging, resolving the actual glowing ring of material and dark shadow at the heart of two separate galaxies. Then came gravitational waves, opening up an entirely new, non-optical channel for detecting black holes colliding across the universe. Each of these advances did not simply confirm what researchers already expected. Each one also introduced new puzzles, new tensions between observation and theory, and new questions that previous generations of researchers had no way of even formulating, since the tools required to notice those questions did not yet exist. The tension between the merger-driven picture of black hole growth and the observations of isolated, undisturbed galaxies hosting unexpectedly massive black holes is a perfect example of this pattern. For years, the picture of galaxies and their central black holes, co-evolving primarily through mergers, fit the available evidence reasonably well, and it took a specifically targeted effort, searching out and carefully measuring black hole masses in galaxies chosen, precisely because they showed no signs of ever having merged, to reveal that this picture was substantially incomplete. That kind of finding does not diminish decades of earlier research. Mergers clearly do drive substantial black hole growth in many galaxies, and the earlier research correctly identified a real and important process. What it reveals instead is that the earlier picture, while genuinely useful and largely correct as far as it went, was not capturing the majority of what is actually happening inside typical, undisturbed galaxies throughout the universe, a majority that appears to be driven by internal processes like spiral arms, bar structures, and inflows from the surrounding cosmic web, mechanisms that researchers are still working to fully quantify and compare against each other, untangling exactly how much each of these internal mechanisms contributes, and whether that balance has shifted meaningfully across cosmic history will likely require exactly the kind of large-scale, repeated, high-resolution observational campaigns that the newest generation of observatories is specifically designed to provide. Continuous brightness monitoring across enormous numbers of actively feeding black holes should help reveal patterns in how accretion rates fluctuate over time, potentially distinguishing between signatures associated with steady internal gas inflow along spiral arms or bar structures versus more episodic inflows associated with mergers or larger-scale cosmic web accretion events. Extremely sharp structural imaging across enormous numbers of galaxies should help build up a much more statistically robust picture of exactly which galaxy shapes correlate with which black hole masses, refining the correlation discussed extensively throughout this discussion with far more precision and far larger sample sizes than previous generations of research were able to achieve, and more detailed radio observations of the outflows and jets produced by feeding black holes should help settle the ongoing debate over whether black hole feedback more often suppresses star formation or occasionally triggers it, a question with direct implications for understanding exactly how and when galaxies transition from actively star-forming to quiet, and whether that transition can, under the right circumstances, reverse itself. There is also a broader lesson embedded in all of this that extends well beyond the specific details of black hole astrophysics. Nearly every major advance described throughout this discussion came from someone noticing a discrepancy between what a well-established theory predicted and what careful, patient observation actually revealed, whether that was an unexpected orbit, an unexpectedly massive black hole in a supposedly undisturbed galaxy, an unexpectedly early population of well-formed disk galaxies, or an unexpectedly common population of mysterious compact red objects turning up in brand new telescope data. None of these discoveries came from assuming the existing picture was already complete and simply looking for more examples that confirmed it. They came from deliberately searching in places where the existing theory made a specific testable prediction, and then paying very close attention when the data did not quite match. This pattern of using very precise theoretical predictions as a kind of tripwire for discovering exactly where our understanding breaks down is, in a real sense, the core method driving essentially all of modern astrophysics forward. And it is exactly this method that continues to reveal, again and again, that even something as intensively studied as supermassive black holes still has a great deal left to teach us. So, where does all of this actually leave us? After tracing the story from a dying star collapsing under its own weight all the way out to the largest, most extreme objects sitting at the centers of entire galaxies, a few things stand out clearly. Black holes are not empty gaps in space, but extraordinarily dense concentrations of matter, fully described by nothing more than their mass, their spin, and their electric charge, with everything else about their history erased behind the event horizon. Supermassive black holes, sitting at the centers of nearly every well-organized galaxy, are tightly and mysteriously linked to the broader properties of their host galaxies, a connection that was long attributed mainly to galaxy mergers, but now appears to depend heavily on internal processes still being actively investigated, from spiral arms and bar structures funneling gas inward, to broader inflows arriving along the cosmic web connecting galaxies across the universe. Growth itself has physical limits, shaped by the interplay between the innermost stable orbit and the self-gravitational radius, limits that may render some of the most massive black holes in the universe permanently invisible to our usual detection methods once they cross a certain threshold. And the very earliest black holes, glimpsed by the James Webb Space Telescope at improbably early points in cosmic history, are forcing a genuine reconsideration of how quickly the first galaxies and their central black holes came together after the universe began. None of these threads are fully resolved. Researchers do not yet know precisely how much of typical black hole growth comes from spiral arms funneling gas inward, versus bar structures doing the same job more efficiently, versus gas arriving fresh from the cosmic web, nor whether the balance between these mechanisms has shifted meaningfully over billions of years of cosmic history. The exact nature of the little red dots recently uncovered by James Webb remains genuinely unsettled, sitting somewhere between a dusty, gas-shrouded feeding black hole and something not yet fully understood, whether primordial black holes exist at all, and whether they might explain some or all of the universe's mysterious dark matter, remains squarely in the realm of hypothesis, awaiting either a confirmed detection or a definitive ruling out. And the deep theoretical tension between general relativities, confident predictions, and quantum physics, insistence that information can never truly be destroyed, continues to await the kind of unified theory of quantum gravity that black hole research is often held up as one of the most promising paths toward eventually discovering. What makes all of this worth following closely is that we are, right now, living through an unusually rich period for gathering exactly the kind of evidence needed to make real progress on these questions. A newly operational wide-field survey telescope is beginning to deliver continuously updated brightness measurements for enormous numbers of actively feeding black holes across the sky. A newly launched space telescope is beginning to deliver extraordinarily sharp structural images of enormous numbers of galaxies, encoding their merger histories in exquisite detail. A next-generation radio telescope array is being constructed specifically to trace black hole outflows and jets in far greater detail than has previously been possible. And the James Webb Space Telescope continues to push observations of the earliest galaxies and earliest black holes further back into cosmic history than researchers previously thought possible, turning up new surprises seemingly every time it looks. Taken together, These efforts represent a genuinely unusual convergence of new instruments, each one specifically targeting one of the open threads discussed throughout this discussion, arriving within roughly the same narrow window of time. It is worth remembering, too, that curiosity about questions this fundamental: how black holes grow, how galaxies live and die, what dark matter actually is, has repeatedly produced practical benefits that reached far beyond the original scientific motivation. From digital imaging technology to wireless networking to medical imaging techniques. That does not mean every piece of curiosity-driven research needs to justify itself through eventual practical applications. There is something genuinely valuable on its own terms in carefully working out the answer to a question as basic as what is actually happening inside the darkest, densest objects the universe produces, and in confronting, honestly and rigorously, just how much remains unknown, even about something studied as intensively as black holes have been. If following along with questions like these, watching how a tightly held scientific picture can shift substantially in the space of just a few years of new evidence, and tracking the genuinely open puzzles still being actively worked on right now is the kind of thing that appeals to you, it is worth sticking around for more of this kind of deep dive into the universe, since there is no shortage of similarly unresolved mysteries still waiting to be untangled. A quick like or a subscribe genuinely helps more of this kind of careful, evidence-based exploration of these questions find its way to more people who are curious about them too. So, if this exploration of black holes and the galaxies they inhabit was worth your time, consider leaving one behind before you go. One additional thread worth returning to briefly is just how strange it is that something making up less than 1% of a galaxy's total mass can end up so tightly correlated with that galaxy's overall structure and history. A useful comparison, though an imperfect one, is to imagine trying to guess the layout and population of an entire city just by weighing its central town hall. Under most circumstances, that would tell you almost nothing useful. Yet, in the case of galaxies and their central black holes, that tiny, disproportionately influential object really does seem to encode meaningful information about the surrounding structure, whether through the shared history of gas inflows that built up both the black hole and the surrounding stellar bulge together, through the disruptive influence mergers have on both simultaneously, or through the feedback effects by which an actively growing black hole can reshape the very gas supply its galaxy depends on for future star formation. Untangling exactly how much of this correlation reflects the black hole actively shaping its galaxy, versus both simply growing in tandem as a byproduct of the same underlying gas supply feeding them together, remains an open and actively debated question in its own right, one that sits underneath much of the more specific research discussed throughout this conversation. It is also worth acknowledging a subtler kind of bias that creeps into nearly every observational study of black holes, given how heavily current detection methods depend on catching a black hole in the act of actively feeding, because only a relatively small fraction of supermassive black holes are actively growing and therefore visible at any given moment, and because the accretion process itself may proceed at different rates in different types of galaxies. There is a real risk that existing surveys are systematically biased toward finding black holes under whichever specific conditions happen to make them easiest to detect, rather than representing a fully accurate cross-section of the true underlying population. Researchers are keenly aware of this challenge, and a considerable amount of effort throughout this field goes into carefully accounting for these detection biases statistically, correcting measured correlations and mass distributions to better reflect the true underlying population rather than simply the subset of objects that that happen to be easiest to spot. This is precisely one of the reasons the incoming flood of data from newly operational wide field survey telescopes is considered so valuable, since a much larger and more complete census of actively feeding black holes, gathered continuously rather than through occasional targeted observations, should help researchers correct for these subtle biases far more effectively than has previously been possible, offering a genuinely more representative picture of how supermassive black holes actually grow across the full diversity of galaxies found throughout the universe. It is also worth noting how much of what astronomers know about the black hole at the very center of our own galaxy came from an extraordinarily patient, decades-long observational campaign, tracking a small handful of individual stars as they trace out tight, fast orbits around an otherwise dark and apparently empty point at the galaxy's exact center. Watching those stars complete full orbits, some of them looping around that invisible point in a span of only a couple of decades, moving at speeds far faster than anything in our own solar system, provided some of the most direct and compelling evidence available anywhere for the existence of a supermassive black hole, since no other explanation could account for stars whipping around empty space that quickly, unless an enormous, extremely compact, unseen mass was sitting right there, pulling on them gravitationally. That patient, multi-decade observational effort, requiring the same handful of stars to be tracked repeatedly across many years using some of the most powerful telescopes on the ground, stands as a reminder that not every advance in this field comes from a single dramatic new instrument or a single sudden discovery. Some of the most convincing evidence comes instead from simple persistence, returning to the same patch of sky year after year until a pattern too consistent to be coincidence finally emerges clearly from the data. The honest summary, after everything covered here, is that black holes remain one of the most productive sources of scientific surprise available to modern astrophysics, not because we know nothing about them, but because we now know enough to notice, with increasing precision, exactly where our current understanding runs out. Every new observatory coming online over the next several years is aimed directly at one or more of the specific open questions traced throughout this discussion. And given how often black hole research has appended its own leading assumptions over just the past few years alone, it would not be surprising if the next round of discoveries reshapes this picture just as substantially as the last one did.